In today's lab, we will be trying to determine the rate law for the reaction of crystal violet with sodium hydroxide. Be sure to read the directions in your lab manual and take the pre-lab quiz before proceeding on with the lab. Recall that a rate law is an expression that helps us to determine the rate of a reaction if the concentrations of the reactants are known. In this case, the concentration of reactant A is the brackets around A, and the concentration of reactant B is the brackets around B. Each of these concentrations is raised to a certain exponent, A to the N, B to the M. That exponent is known as the order with respect to that reactant. So the order with respect to A is N, and the order with respect to B is M. The rate law must be determined experimentally and cannot be determined just by looking at the chemical equation. We want to be able to look at the rate law by determining just one reactant at a time. One way we can do this is by making the concentration of one of the reactants so great that even though the reaction proceeds, the change in that concentration is very small and won't affect the overall change in the rate. Our reaction today is with crystal violet. We will be using the shorthand CV+ to represent crystal violet, and as the name implies, it is a purple compound. Our reaction, as described in your lab manual, will be between crystal violet and hydroxide, forming a complex that is crystal violet hydroxide. Our reaction today will take the form of the rate being equal to a rate constant times the concentration of crystal violet raised to the power of N times the concentration of hydroxide raised to the power of M. In today's reaction, we will keep the hydroxide fairly constant by having an overabundance of it. In this way, even if there are small changes in it, because of the high concentration, the overall concentration will not change much. So this last equation will represent what we are doing today. Everything in the parentheses can be represented by K prime. So our rate constant really includes the concentration of hydroxide. We will only then be looking at the concentration of crystal violet. To determine the concentration, we will need some method to quickly and easily determine the concentration as the reaction continues to proceed and the concentration changes. Because crystal violet is purple in color, we can use the absorbance and Beers Law. Remember that absorbance is equal to the concentration times the cell length times the absorptivity. Because the cell is 1 centimeter, we can take that out, and our concentration is going to be, in brackets, CV+. In this way, the absorbance will be proportional to the concentration of crystal violet. So we will use the absorbance to determine the rate pattern. It is important that we have a proper wavelength of light that is being absorbed. Remember that whatever color something appears, we need to be looking at the absorbance of a color opposite on the color wheel. For our colorimeter, the closest color to this is green, and we will be looking at 565 nanometers. For this lab, you will be using 0.02 molar sodium hydroxide, a prepared crystal violet solution, 10 milliliter graduated cylinders, beakers, an ice bath, and cuvettes. We will be using Logger Pro, and you will be using the colorimeter that goes with Logger Pro. The setting on the calorimeter should be 565 nanometers. These cuvettes are a little different than the cuvettes we've used in other labs. You'll notice first they are square. There is a side that has ribbing on it and a side that is smooth. We want to avoid touching the smooth side because this is the side that light will pass through. Your lab manual refers to a reference mark. Sometimes you will see at the top of one of the edges a triangle. If not, just make sure that you face one of the clear sides towards the reference mark in the calorimeter.